Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Okay, let's unpack this. Because right now, if you look at our galaxy, there are roughly 100 billion planets out there.
Yeah, mathematically speaking, the Milky Way is just incredibly crowded.
Right. And since 1992, we've gone from just wondering if other planets even existed to actually confirming over 6,000 of them.
With like 7,000 more just sitting there awaiting confirmation.
Exactly. So the statistical reality is basically one exoplanet for every single star in the sky. But we aren't spending billions of dollars just to find inert spheres of gravel, you know.
No, definitely not.
We're looking for life. And the ultimate bottleneck for life, the absolute ultimate cosmic filter, is whether a planet can actually hold on to an atmosphere.
Which is a far more precarious mechanism than I think most people realize. Because when we looked at that massive volume of exoplanets, the assumption is usually that habitability is just about orbital distance.
Like the classic Goldilocks zone.
Right, the habitable zone.
Yeah.
Not too hot, not too cold, so liquid water can exist. But this new modeling research totally shifts that paradigm inward.
Yeah, specifically the research spearheaded by Michelle Hill and her colleagues over at the Stanford Dewar School of Sustainability.
Exactly. They're focusing on the internal geodynamics of a planet, asking what actually dictates a planet's ability to not just get an atmosphere, but actively defend it.
Defend it against its own star, which is huge because, we can't exactly send a probe 40 light years away to scoop up microbes.
Right, we rely entirely on spectroscopic analysis.
Waiting for the planet to pass in front of its star, catching that filtered starlight, and looking for, chemical barcodes of life.
Methane, oxygen, things like that.
But that whole plan goes out the window if the planet has already been stripped bare. So we need to understand the mechanics of that loss. Because I think a lot of people view a planetary atmosphere as just this permanent fixture.
Yeah, like you have gravity, it pulls the gas down, and that's the end of the story.
Exactly. But it's not.
No. The reality is much closer to this violently contested equilibrium. An atmosphere isn't a static envelope, it's basically a battleground.
It's like a cosmic tug of war. The planet's gravity is desperately pulling this atmospheric blanket tightly around itself, while the star is this incredibly aggressive wind just trying to rip it right off.
That's a perfect analogy. You have the planet's mass dictating its gravity on one side, and the host star blasting intense radiation on the other. And we have to look at this thermodynamically.
Okay, break that down for me.
So a gas is really just a collection of molecules in constant motion. And the temperature of that gas is just a measure of the average kinetic energy of those bouncing molecules.
Right.
So to keep the atmosphere, the planet's escape velocity, which is purely about its mass and physical radius, has to stay significantly higher than the velocity of those gas molecules up in the upper atmosphere.
So if the star heats up that upper layer, the gas molecules start moving faster.
Exactly.
And if they move faster than the planet's escape velocity, they just kind of bleed off into the vacuum of space.
Yeah, that's the baseline thermal escape. It's often called Jean's escape. But the stellar environment is way more aggressive than just ambient heat.
Right. It's not just a slow leak.
No, we have to look at extreme ultraviolet and X-ray spectrums, what astrophysicists call XUV radiation.
All right.
When a rocky, volcanically active planet forms, its main greenhouse gas is usually carbon dioxide. And CO2 is a relatively heavy, really stable molecule.
So in a vacuum, gravity holds it down pretty well.
It does. But when that planet gets absolutely bombarded by high-energy XUV photons from its host star, we get this process called photodissociation.
Okay, wait, let me stop you there because the mechanics of photodissociation usually get totally glossed over.
Sure.
So the photon hits the CO2 molecule. I'm picturing like a cue ball hitting a cluster of billiard balls and just shattering the chemical bond.
That's a good visual.
But why do the individual oxygen and carbon atoms suddenly have enough kinetic energy to launch themselves into space? Breaking a bond takes energy. It doesn't just magically create outward momentum.
That is a really crucial distinction to make. So the energy of an incoming X-ray or extreme ultraviolet photon is actually way greater than the binding energy of the bonds in that CO2 molecule. Oh, I see.
The photon shatters the bond, yes, but the excess energy from that photon doesn't just disappear. The laws of thermodynamics say it has to be conserved.
Right.
So that excess energy gets converted directly into the kinetic energy of the resulting fragments. The carbon and oxygen atoms literally fly apart at incredible velocities.
Wow. So they essentially act like molecular shrapnel.
Exactly the right visual. And you have to factor in the mass of those particles, too. An intact carbon dioxide molecule has a molecular mass of 44 atomic mass units.
So it's heavy.
Heavy, sluggish, requires a massive amount of energy to hit escape velocity. But when you shatter it, you're left with an oxygen atom at 16 mass units and a carbon atom at 12.
And because kinetic energy is, what, 1/2 mass times velocity squared?
You got it. A lighter particle with that exact same energy is going to travel at a significantly higher velocity.
So these fragmented, lighter atoms are suddenly rocketing upward fast enough to break the gravitational tether?
Yes, they just shoot right out. But wait, the atmosphere isn't just an empty highway, right? It's densely packed with a ton of other molecules.
Right.
If this carbon atom is rocketing upward, it's going to crash into other gases on its way out.
It definitely does. And that introduces something called hydrodynamic drag.
Okay, what does that look like?
As these hyper-accelerated lighter atoms race outward, they physically slam into heavier, slower-moving molecules in the upper atmosphere. And during those collisions, they transfer some of their kinetic energy.
Like a domino effect.
Kind of, yeah. If the flux of these escaping light atoms is dense enough, they actually create an outward macroscopic flow.
Oh, wow.
They literally drag heavier molecules, including perfectly intact greenhouse gases and water vapor, right out into space with them.
So it's not just the broken pieces escaping, they're pulling the good stuff out with them.
Exactly. Under the right stellar conditions, it's not a slow leak. It is a catastrophic accelerating drain.
Which means the planet's physical size is really the absolute deciding factor here. Because if gravity is the only anchor pulling against this XUV-driven hydrodynamic escape, you need a certain critical mass to survive it.
You do. And that brings us to the core modeling done by that team at Stanford. They basically set out to find the exact size cutoff.
Like, exactly how big does a rocky planet need to be to survive this absolute onslaught?
Right. And to figure that out, they use a computational framework called exoplex.
I want to dig into how you actually model a planet that's thousands of light years away. Because, I mean, you can't just stick it in a wind tunnel.
No, you definitely can't. Exoplex is this highly sophisticated Python-based thermodynamic modeling tool. It doesn't look at the planet through a telescope. It mathematically builds the planet from the inside out.
Because our observational technology is actually pretty limited.
Very limited. Yeah. When we find an exoplanet, we basically only get 2 pieces of data.
Radius and mass.
Exactly.
Okay.
We get the radius based on how much starlight it blocks when it transits, and the mass based on how much its gravity makes the host star wobble.
But knowing a planet is, like, identical to Earth in mass and radius doesn't tell us what it's actually made of.
No, it could be a giant sphere of water or just a solid ball of iron with a super thin crust.
Right. So how does Exoplex figure that out?
That's where equations of state come into play. Exoplex takes those basic observational inputs and applies fundamental physics to calculate the internal pressure profiles.
Okay.
Because as you move deeper into a planet, the immense weight of the overlying rock compresses all the material below it, and the equations of state describe exactly how different minerals like silicates or iron alloys compress and change phase under millions of atmospheres of pressure.
So it's simulating the crunch.
Yeah. By running those calculations, Exoplex can generate an incredibly accurate profile of a planet's internal structure. It gives you the exact radius of the iron core, the thickness of the rocky mantle, and the surface gravity.
So for this specific investigation, Michelle Hill's team generated 6 different planet profiles using this tool.
They did. And they focused entirely on rocky planets, specifically what geophysicists call stagnant lid planets.
You definitely need to define that. Because Earth is absolutely not a stagnant lid planet.
No, Earth has a mobile lid. We experience it as plate tectonics.
Right. Our crust is fractured into massive plates that shift around, dive beneath each other at subduction zones, and basically recycle material deep into the mantle.
Exactly. But a stagnant lid planet is different. It has a single, continuous, rigid outer shell. The crust does not shift.
It's just a solid, unbroken sphere of rock locking the whole interior away.
Yes. And that seems to be the default state for most rocky bodies we observe. Mars is a stagnant lid. Venus is a stagnant lid. Even our moon.
Earth really is the weird outlier with its cracked shell.
It is. So the researchers used stagnant lid planets as their baseline for the simulation. They equipped them with thick carbon dioxide atmospheres, and they tested a really specific size range.
What were the sizes?
They started at exactly the size of Earth, which they denote as 1.0 Earth radii, and they incrementally scaled the models down to half the size of Earth. So 0.5 Earth radii.
Okay, and then what?
Then they subjected these virtual models to billions of years of simulated stellar radiation just to find the breaking point.
See, I would have intuitively guessed that atmospheric loss operates on a fairly smooth curve.
How do you mean?
Like a 0.9 Earth radii planet holds its air just a little bit less efficiently than a 1.0. And a 0.8 holds it a bit less than a 0.9, just this gradual slide into oblivion.
That's a logical assumption, but it's not what happened. The exoplex simulations revealed this massive cliff edge.
Here's where it gets really interesting. What was the threshold?
The critical threshold is exactly 80% of Earth's radius, 0.8.
Wow.
Yeah. If a planet is 0.8 Earth radii or larger, it can successfully anchor its atmosphere against the stellar wind for 10 billion years.
Assuming it orbits a stable sun-like star at a comfortable distance?
Right. The gravity generated by that specific mass profile is just strong enough to keep the escape velocity higher than the kinetic energy of all those photo-dissociated fragments we talked about.
But the moment you drop below that 0.8 threshold, like if you look at a 0.75 or a 0.6 Earth radii planet, the timeline just collapses.
Completely collapses. They don't lose their atmosphere in 9 billion years, or even 8 billion years.
They get completely stripped bare within a mere 1 billion years.
Yes, it is an exponential drop in viability.
Which is wild. Why is that specific temporal difference, 1 billion versus 10 billion years, so crucial? Like, why is that the ultimate filter for biology?
Well, we have to look at time through an evolutionary lens. Because a billion years sounds incomprehensibly long to us.
Right. Human history is a blink compared to that.
Exactly. But geologically speaking, a billion years is just a planetary infancy.
Okay, trace the timeline of a newly formed world for me.
So a planet accretes from these incredibly violent collisions of planetesimals and protoplanets in the early solar system. And all the kinetic energy of those massive impacts gets converted straight into heat.
So for the first few 100 million years, a rocky planet is basically just a molten ball of magma.
Exactly. It's entirely hostile. You can't have liquid water, let alone fragile organic chemistry, when the surface is literally a liquid rock ocean.
All right, so it has to cool down first.
It has to cool. The magma ocean has to crystallize into a solid crust. The volatile gases have to outgas to form an early atmosphere.
And then it has to cool even more for water vapor to actually condense and rain down to form the first oceans.
Yes, and that initial cooling and stabilization phase alone can eat up a huge fraction of that first billion years.
And early solar systems are super chaotic, right?
Oh, incredibly chaotic. Planets are frequently subjected to things like the Late Heavy Bombardment,
which is just a period of intense asteroid and comet impacts.
Right. Impacts so massive they can repeatedly sterilize the surface and literally boil early oceans right back into vapor.
So if your atmospheric retention limit is only 1 billion years, your planet is basically spending 900 million years just trying to calm down enough to form a puddle.
Exactly. And the moment it finally stabilizes, the atmosphere just runs out.
It's a biological false start.
It really is. Even if we assume the RNA world hypothesis is just incredibly efficient-like, even if basic single-celled, self-replicating molecules manage to spark into existence in those newly formed oceans the exact second the temperature allows it,
they immediately face a terminal crisis.
Yes. As the atmospheric pressure drops because of the stellar stripping, the boiling point of water decreases. The oceans literally begin to evaporate.
And losing the ozone and CO2 layers means lethal levels of ultraviolet radiation start hitting the surface.
Which just breaks down any fragile nucleotide bonds. A 1 billion year window basically ensures the planet dies before evolution can even begin to iterate.
While 10 billion years gives you the deep time required for real complexity.
Right. On Earth, it took life roughly 3 billion years just to figure out how to be multicellular.
Evolution isn't some rapid engineering process. It's a blind, statistical mechanism of trial and error. It needs a stable theater.
Exactly. That 0.8 Earth radii threshold isn't just some astrophysical curiosity. It is the dividing line between an inert rock and a potential cradle for civilization.
But, up until now, we've kind of been treating the atmosphere as this finite resource. Like the planet is issued a single tank of gas when it forms, and once it leaks out, it's just gone forever.
Right, but that isn't how planets actually work. A planet is a dynamic geological engine. It basically creates its own air.
Which brings us to the concept of the planetary carbon cycle. This is so fundamental to long-term habitability.
It really is. As we discussed, carbon dioxide is the vital greenhouse gas for these worlds. But CO2 doesn't just remain permanently suspended in the atmosphere.
It's constantly subject to chemical weathering. Walk me through the chemistry of that weathering. Because it's not like the wind is just blowing the carbon away. It's an active chemical sink.
Right. Let's trace a carbon dioxide molecule on a temperate, water-bearing planet. The CO2 in the atmosphere dissolves into rainwater, which forms a very weak carbonic acid.
Okay.
When the slightly acidic rain falls onto the silicate rocks of the planet's crust, it triggers a chemical reaction. The carbonic acid breaks down the silicate minerals.
And that releases what? Calcium and magnesium ions.
Exactly. Those ions, along with bicarbonate, get washed by rivers straight into the oceans,
Where they eventually precipitate out.
Through a series of marine reactions, the calcium and bicarbonate combine to form calcium carbonate, which is basically limestone.
Okay, so this solid calcium carbonate sinks to the ocean floor and gets buried.
Yes. The crucial takeaway here is that the atmosphere is constantly, actively losing its carbon dioxide.
The gas is literally being scrubbed from the sky and locked away in solid rock in the bottom of the sea.
Exactly. If there was no mechanism to reverse that process, a planet would strip its own greenhouse shield within a few million years. It would just plummet into a global ice age.
So the planet has to actively breathe the CO2 back out. It needs an exhaust system.
And that exhaust system is volcanism.
Volcanoes.
Right. Volcanoes are the primary mechanism of atmospheric replenishment. Deep within the planet, the pressure and heat melt those carbon-rich rocks.
The magma rises.
And as it depressurizes near the surface, all that trapped carbon dioxide is vented right back into the atmosphere.
Which reinflates the planetary shield and completely closes the carbon cycle.
Exactly.
But volcanoes do not erupt by magic. They require an immense, continuous source of internal thermal energy to keep the rock in the mantle viscous enough to actually convect and rise.
Yes, they do.
And you can't just rely on the leftover heat from the planet's initial formation, right?
No, definitely not. That primordial heat would dissipate far too quickly. The planet needs an internal battery.
And it needs a radiogenic heat source.
Exactly. When we talk about the long-term survival of a planet, we're really talking about the radioactive isotopes embedded deep in its rocky mantle.
Specifically, we're looking at three main isotopes: thorium-232, uranium-238, and potassium-40.
Yes.
And I think most people associate uranium with, like, human-made nuclear reactors or weapons. The idea that a planet is naturally functioning as this slow-burning nuclear reactor is a bit alien.
It is, yeah.
How did this radiogenic heating actually work on a massive geological scale?
Well, it's governed by the basic physics of nuclear decay. These isotopes are fundamentally unstable.
Okay.
Over massive timescales, which are dictated by their half-lives, their atomic nuclei spontaneously break apart to try and reach a more stable configuration.
Right.
Uranium-238, for instance, undergoes alpha decay. It ejects an alpha particle, which is essentially just a helium nucleus made of 2 protons and 2 neutrons at a very high velocity.
And when that high-velocity alpha particle slams into the surrounding silicate rock, the mantle, its kinetic energy gets converted into thermal energy.
Exactly. It's basically friction, just at a subatomic level.
Wow.
And a single alpha decay produces a truly infinitesimally small amount of heat.
But you have trillions upon trillions of tons of uranium, thorium, and potassium scattered throughout the entire mantle.
Exactly. The cumulative thermal output is just staggering. This radiogenic heat provides the continuous billion-year energy source needed to keep the mantle semi-molten.
Which drives the massive convection currents that slowly churn the deep rock, pushing magma toward the surface to fuel the volcanoes.
Right.
Think of the planet like a slow-release heat pack. The radioactive elements are the chemical fuel inside, and the volcanoes are the exhaust vents keeping the atmospheric bubble inflated.
That's a great way to put it.
So it keeps the CO2 venting,
Yeah.
which keeps the atmosphere inflated, which keeps the surface warm enough for water, which allows life to survive. It's this incredibly delicate chain of dependency.
It really is.
But there is a fatal flaw in this system. Radioactive decay is a one-way process.
Right. It has an expiration date.
Isotopes have half-lives. Uranium-238 has a half-life of roughly 4.5 billion years. Potassium-40 has a half-life of about 1.25 billion years.
And as these elements decay into stable daughter products like lead or argon, they completely stop producing heat.
So the planet's radiogenic fuel supply is totally finite, and it's constantly diminishing from the exact moment of formation.
Every planet is basically born with a ticking clock. When the initial supply of uranium, thorium, and potassium drops below a critical threshold, the heat output just can't overcome the natural thermal loss to space anymore.
The mantle cools down.
The convection currents stall. The internal engine basically seizes up.
The rock hardens, and volcanism just ceases entirely.
And without volcanoes venting new carbon dioxide to replace the gas being scrubbed by weathering or stripped by stellar winds, the atmospheric shield collapses.
Which brings us to one of the most fascinating and honestly counterintuitive discoveries from the exoplex modeling regarding a planet's internal structure.
Right, about the core size.
Because if radiogenic heat is the currency of planetary survival, you'd naturally assume that you want a planet with the absolute highest mass possible, which usually means a massive, dense iron core. More gravity, more mass, more stability.
It seems perfectly logical, but the geophysics reveals the exact opposite. A massive iron core is actually a massive detriment to long-term habitability.
That is so wild. Why?
To understand that, we have to look at the geochemistry of planetary differentiation.
Okay.
When a rocky planet first forms and is still in its initial magma ocean phase, all the heavy elements sink to the center to form the core, and the lighter elements float to the top to form the mantle and crust.
Like oil and water separating.
Exactly. But chemical elements behave differently based on their specific atomic properties. Uranium, thorium, and potassium are what we classify as lithophile elements.
Lithophile, meaning rock-loving.
Precisely in their chemical behavior. Due to their ionic radii and their electronegativity, they do not bond well with metallic iron at all.
Oh, interesting.
They cannot easily dissolve into that sinking iron-nickel alloy that forms the planet's core. Instead, they strongly prefer to bond with oxygen and silicon to form silicate minerals.
So they stay in the rocky parts.
Yes. During the planet's molten differentiation phase, almost the entire inventory of the planet's radiogenic isotopes gets pushed out of the core and concentrated exclusively in the rocky mantle.
So the core is functionally completely devoid of radioactive fuel. It's just a massive sink of dense metal.
Right. So if a planet forms with an exceptionally large iron core, it mathematically must have a thinner, smaller rocky mantle.
Because the core is taking up all the room.
Exactly. It has less physical storage volume for those crucial lithophile elements.
It's like having a car where 80% of the chassis is just solid steel weight, leaving only this tiny little space for the actual gas tank.
That's exactly it. The internal geometry is a major determining factor in atmospheric retention. A planet with a relatively smaller core and a massive, thick, deep mantle acts like a much larger battery.
It can hold a significantly higher concentration of radiogenic fuel per unit of planetary volume,
which allows it to run its internal volcanic engine, maintaining those convection currents and replenishing its carbon dioxide shield for billions of years longer than a planet with a massive core.
That fundamentally changes how we target exoplanets. We aren't just looking for 0.8 Earth radii worlds anymore. We're looking for planets with the correct core-to-mantle ratios to guarantee they actually have enough fuel to survive their own timeline.
It adds a whole new layer of complexity to the search, absolutely.
But if internal heat is the ultimate savior here, there's an obvious paradox.
The hot start paradox.
Yeah, because if a thick mantle full of heat-producing isotopes is good, then a planet that starts off incredibly hot should be in the best possible position, right? A massive surplus of initial energy.
You'd think so. But in planetary dynamics, starting too hot is basically an automatic death sentence.
Okay, walk me through that. Why is starting hot so dangerous?
It perfectly illustrates the temporal complexities of planet formation. We really have to consider the state of the host star during the planet's infancy. When a star like our sun first ignites, it is not the calm, steady yellow dwarf we experience today. It goes through what's known as the T-Tauri phase.
And T-Tauri stars are violently unstable.
Extremely. They're rotating incredibly rapidly, often completing a full rotation in just a matter of days rather than weeks.
Wow.
And that rapid rotation generates a wildly twisted, hyperactive magnetic field. As a result, a young T-Tauri star produces stellar flares and extreme ultraviolet radiation at levels thousands of times higher than a mature star.
So it's basically throwing a billion-year-long temper tantrum.
That's an accurate description. The star's ability to strip a planetary atmosphere via that hydrodynamic escape we discussed earlier is at its absolute maximum during its youth.
Okay, so put our hot start planet next to that angry young star.
Right. Consider a hot start planet orbiting this aggressive star. If a planet forms with internal temperatures that are far too high, maybe due to a massive abundance of short-lived radioactive isotopes like aluminum-26, or just the kinetic energy of too many massive impactors.
The entire mantle just remains a liquid magma ocean.
Yes. And liquid rock does not trap gas.
Wait, really?
Liquid magma has a vastly lower solubility for volatile gases than solid rock does. A magma ocean violently and rapidly outgasses its entire inventory of water and carbon dioxide.
So it pushes all this air out immediately.
Exactly. It creates this incredibly thick, dense atmosphere extremely early in the planet's life.
Which sounds great until you look at the calendar.
Precisely. The planet has exposed its entire atmospheric shield precisely when the host star is in its violently destructive T-Tauri phase.
The peak atmospheric outgassing perfectly aligns with the star's peak atmospheric stripping power.
The XUV radiation just obliterates the newly formed atmosphere, severing the molecular bonds and sweeping all those fragments right into space.
It basically blows through its entire atmospheric budget while the star is at its absolute most destructive.
Furthermore, a liquid mantle is incredibly efficient at transferring heat to the surface via rapid convection. Yeah, the planet essentially dumps all of its internal thermal energy into space. In a fraction of the time, it would take a solid mantle to slowly, gradually release it.
So it burns the candle from both ends, it loses its air, and it loses its internal heat simultaneously.
Exactly. By the time the host star finally matures and settles into a stable, calm sequence, the hot start planet is already dead.
Its radiogenic battery is totally depleted.
Its mantle is frozen solid, and its volatile gases are scattered across the solar system. It ends up just a sterile, barren rock for the rest of eternity.
So what does this all mean? We're dealing with an incredibly complex, temporal, habitable zone.
It's not just about space anymore.
Right. We all know the spatial habitable zone, the orbital distance where water doesn't boil or freeze. But the Stanford models reveal a timeline lock.
A timeline lock. I like that phrasing.
You need the planet's external orbit to be correct, but you also need the planet's internal timeline to precisely match the star's external timeline.
Exactly. The planet must hold its volatile gases deep inside its solidifying mantle, regulating its heat, just waiting patiently through the star's violent youth.
It can only afford to steadily vent its atmosphere once the star has calmed down enough not to instantly rip it away.
The synchronization required is staggering. A planet can be the perfect size. It can have the exact 0.8 Earth radii mass. It can have the ideal core-to-mantle ratio. It can be sitting in the dead center of the spatial habitable zone.
But if its internal geological clock runs too fast early on, it's just removed from the equation.
Completely.
Which forces us to ask a difficult question about the reliability of this entire theoretical framework.
How so?
Well, we are applying complex equations of state, hydrodynamic drag calculations, and radiogenic half-lives to exoplanets that are really just flickering pixels of light on our sensors.
Right. It's all highly theoretical.
If this code is going to dictate how we search for life in the galaxy, we need to know if it actually works in our own solar system.
And that is exactly how Michelle Hill and the Stanford team validated the exoplex models. Before they started applying the code to distant exoplanets, they actually turned the simulation inward.
They used it to analyze our immediate neighbors, Venus and Mars.
The ultimate test cases.
Because they represent the extreme ends of the atmospheric spectrum, right?
Exactly. You have Venus, which is this greenhouse hellscape with an atmosphere so thick and heavy, the surface pressure would crush a nuclear submarine.
And then you have Mars, which possesses an atmosphere so incredibly thin, it basically barely registers as a vacuum in a laboratory setting.
So the researchers inputted the known baseline geophysical data for both planets straight into the model. They provided the mass, the radius, the estimated core-to-mantle ratios, and the solar flux based on their orbital distances.
And then they just let the simulation run a multi-billion-year thermodynamic projection.
Yes.
Did the math hold up?
It was remarkably accurate. The model correctly predicted that Venus, with a radius of approximately 0.95 Earth radii, falls well above that critical 0.8 threshold.
And coupled with its massive, deep mantle.
The simulation showed Venus would easily generate and retain a thick, enduring carbon dioxide atmosphere, exactly as we observe today.
Okay, but what about Mars?
The model confirmed the exact opposite outcome for Mars. At roughly 0.53 Earth radii, Mars falls drastically below the survivability threshold.
So the math works.
It does. The simulation accurately mapped out the accelerated dissipation of the Martian atmosphere.
Let's dig into the specific pathology of Mars's death, because this directly challenges a massive cultural obsession right now.
You mean terraforming?
Exactly.
Yeah.
Mars wasn't just a random data point for this study. Mars was the inspiration. We have an entire subculture of billionaires, science fiction writers, and space enthusiasts pushing the narrative that we're going to terraform Mars.
It's a very popular idea.
The prevailing narrative is that Mars is just dormant. Like if we can just nuke the polar ice caps or build giant greenhouse gas factories, we can pump a new atmosphere into the sky and turn the red planet green.
It is often treated as a purely engineering problem. Like, we just need enough money and technology.
Right. But the STEM models provide a very sobering thermodynamic reality check to those aspirations.
They really do. The issue with terraforming Mars is not the logistical hurdle of manufacturing the gas. I mean, you could theoretically liberate the frozen CO2 in the regolith. The insurmountable physics problem is retention.
Because you are actively violating thermodynamic equilibrium.
Exactly. Mars's internal radiogenic engine is dead. Its mantle cooled billions of years ago.
It lacks the internal heat required to maintain a liquid outer core, which means it cannot generate a global magnetic dynamo to deflect the solar wind.
That's part of it. But even more critically, the planet simply lacks the mass to generate the necessary surface gravity.
Hold on, I want to clarify something here. Because when people talk about Mars losing its atmosphere, they almost always blame the loss of the magnetic field.
Right, that's the common narrative.
The story goes that once the core froze and the magnetic field died, the solar wind just sandblasted the air away. But this research implies gravity is actually the primary culprit.
The role of planetary magnetic fields and atmospheric retention is actually a subject of intense debate in modern astrophysics.
Really?
Yeah. A magnetic field does deflect the primary solar wind particles around the planet. However, the magnetic poles also create these funnels where solar energy can directly interact with the upper atmosphere, which can potentially accelerate ion escape.
Oh, so it might actually make things worse in some ways.
It's complex, but the Stanford research focuses on the sheer physical mass. Regardless of whether a magnetic field is present or not, if the planet's escape velocity is too low, the XUV radiation will photodissociate the molecules and the thermal energy will drive them into space.
Gravity is the ultimate boss.
Gravity's the boss.
So even if we performed an engineering miracle, even if we manufactured a dense Earth-like atmosphere tomorrow, complete with nitrogen and oxygen, and draped it over Mars,
it would not stabilize. Without the requisite gravity, the solar XUV radiation would immediately begin tearing that artificial atmosphere apart.
the ultraviolet light would shatter the molecules, the lighter atoms would reach escape velocity.
And the massive hydrodynamic drag would sweep the heavier elements away. You wouldn't be creating a permanent habitat. You would just be temporarily feeding the solar wind.
The atmosphere would constantly bleed into the vacuum, meaning humanity would have to endlessly manufacture millions of tons of gas per day just to replace what physics is actively stripping away.
It is exactly akin to trying to fill a bucket that has massive holes in the bottom.
That is brutally definitive. Mars is a stagnant lid planet that lost its cosmic tug-of-war billions of years ago.
It did.
But repeatedly, using that phrase, stagnant lid, brings us to a crucial realization about our own existence. Because Earth is not a stagnant lid planet.
No, we have a mobile lid. We have plate tectonics.
And when you look at the incredibly narrow margins of survivability for a stagnant lid planet, it makes you realize how utterly bizarre our own geology is.
Plate tectonics is arguably the most vital and statistically the rarest geological feature a rocky planet can possess. It fundamentally alters the carbon cycle we discussed earlier.
Because on a stagnant lid planet, the carbon cycle is this crude, one-way system.
Right. Weathering pulls carbon down, and if the radiogenic battery is still running, random hotspot volcanism pushes it back up.
It's clumsy. There is no regulation.
But a mobile lid acts as a massive, continuous geological conveyor belt. As the tectonic plates shift and collide, the oceanic plates, which are laden with all that sunken calcium carbonate limestone, are forced down into the fiery mantle at subduction zones.
And the immense heat and pressure melt the limestone, liberating the carbon dioxide.
Which is then vented back through volcanic arcs like the Ring of Fire.
So plate tectonics acts as a planetary thermostat. If the planet gets too hot, weathering increases, scrubbing more CO2 from the sky and cooling the planet down.
And if the planet gets too cold?
Weathering slows down, but the tectonic conveyor belt keeps subducting and venting CO2, building the greenhouse effect back up until the ice melts.
It is a highly responsive, self-correcting mechanism. It has stabilized Earth's climate for nearly 4 billion years, buffering us against extreme variations in solar output and internal radiogenic decline.
Which is incredible.
And the next phase of this research will actually involve creating complex exoplex profiles for mobile lid planets to compare their longevity against the stagnant lid baseline.
But even before those new models are finalized, the sheer complexity of the stagnant lid models forces a profound philosophical shift.
What do you mean?
Well, when you stack up the requirements, you need a mass greater than 0.8 Earth radii. You need a highly specific core-to-mantle ratio to maximize lithophile isotope storage.
You need to avoid the hot start paradox during the star's volatile youth.
Right. And ideally, you need the incredibly rare mechanic of a mobile crustal lid. It changes how we contextualize the search for extraterrestrial life entirely.
It shifts our analytical framework from a purely spatial domain to a deeply temporal one.
Exactly. I want to read a quote from Michelle Hill regarding this exact timeline realization.
Go for it.
After running these billions of years of simulations, she noted, maybe the answer to why we haven't found any life yet is that we're so early in the grand scheme of what has been created through the lives and deaths of stars. Maybe we're one of the first.
That is a concept that demands serious astrophysical unpacking.
It carries an immense weight. The Fermi paradox asks, if the universe is so vast, where is everyone? We spend all our time pointing telescopes at the sky, asking where the alien life is.
We just assume the Milky Way should be teeming with sprawling civilizations right now.
But this research suggests we are asking the wrong question. We shouldn't be asking where the alien life is. We should be asking when the alien life is.
Wow.
We might be searching for a crowded galactic party, but we arrived 4 billion years before anyone else even got dressed.
To understand why we might be early, we have to look at the cosmological timeline and the metallicity of the universe.
Okay, let's look at it.
The building blocks required to satisfy the Stanford survivability model literally did not exist at the dawn of time.
Because the universe started with the Big Bang, which only produced hydrogen, helium, and a tiny trace of lithium.
Right. There was no carbon for atmospheres, no silicon for rock, and certainly no uranium for radiogenic heat.
None of it.
Precisely. We categorize stars by their metallicity. Astrophysicists call any element heavier than helium a metal. The very first generation of stars, population third stars, were massive, incredibly hot, and made entirely of hydrogen and helium.
They had no rocky planets because there was no rock.
Exactly. When these massive stars exhausted their fuel, they died in violent supernova explosions.
And the intense heat and pressure of those supernovas forged the heavier elements, carbon, oxygen, iron, and blasted them out into the cosmic dust clouds.
But even a standard supernova is not sufficient to create the heaviest radiogenic elements that power planetary mantles.
Wait, really?
Elements like uranium and thorium require highly specific, extreme astrophysical events to form.
Such as neutron-star mergers.
Yes. The rapid neutron capture process, or ARP process, which occurs when two incredibly dense neutron stars collide, is required to forge these heavy, unstable isotopes.
And those events are rare.
Very rare. It took billions of years and multiple generations of stars living, dying, and merging just to seed the galactic medium with a sufficient concentration of lithophile radiogenic isotopes to even allow a planet with a functional internal engine to accrete.
So the universe had to spend the first several billion years of its existence merely manufacturing the fuel.
Exactly. The raw materials for a survivable planet simply weren't available in sufficient quantities until relatively recently in cosmological terms.
Earth formed roughly 4.5 billion years ago, which is about 9 billion years after the Big Bang. We coalesced from a dust cloud that was heavily enriched by the remnants of ancient supernovas and neutron star collisions.
We achieved an incredibly rare, perfectly timed statistical balance.
We hit the 1.0 Earth radii mass requirement.
We acquired the exact necessary dosage of radiogenic fuel to power our mantle.
We somehow developed the mobile tectonic lid to regulate our carbon cycle.
And we managed to hold our volatile gases deep inside long enough to survive the volatile youth of our sun.
When you synthesize all the geophysics, the chemistry, and the stellar dynamics we've explored today, It highlights how truly unique Earth is among the thousands of discovered exoplanets.
We are the beneficiaries of an impossibly long, highly specific chain of cosmic prerequisites.
If biology requires all of these exact chronological and thermodynamic tumblers to click into place in sequence, it is entirely plausible that we are not late to the galactic community.
We might be the elders.
We might be the very first microbes to successfully claw our way out of the gravity well.
It fundamentally reframes the Copernican principle. We assumed we were completely average, orbiting an average star in an average galaxy.
But thermodynamically speaking, a survivable, enduring atmosphere is the rarest of sanctuaries in a violently hostile universe.
It truly is.
Let's pull all these threads together because the sheer scale of the mechanics we've discussed completely rewrites how we should view planetary habitability.
Absolutely.
We started with a staggering number 100 billion planets in the galaxy, but we learned that habitability is not just about finding a rock orbiting at the right distance from a star.
There is a strict mathematical survivability cutoff. A planet must be at least 80% the size of Earth, 0.8 Earth radii, to generate the gravitational anchor needed to prevent its atmospheric fragments from reaching escape velocity when bombarded by stellar X-rays.
And we uncovered the hidden radiogenic engine. A planet is not a static rock, it is a thermal battery.
It must possess a thick mantle packed with incompatible lithophile elements, decaying uranium, thorium, and potassium to keep its interior molten.
Which drives the convection currents that fuel the volcanoes, continuously venting carbon dioxide to replace what is lost to chemical weathering and hydrodynamic escape.
And we explored the temporal paradox of a hot start. A planet cannot afford to melt its mantle and outgas its atmosphere too early, or it exposes its fragile greenhouse shield to the violently destructive magnetic flares of its young T-Tauri phase host star.
And we face the thermodynamic reality check of Mars. The red planet isn't a dormant world waiting to be terraformed. Its small size and depleted radiogenic battery mean its escape velocity is too low.
Physics dictates that any atmosphere we attempt to engineer there will be systematically stripped away by the solar wind.
The overarching takeaway is that an atmosphere is a billions of years long balancing act between internal heat generation and external stellar assault.
It is an ongoing war.
So, to you, listen to this right now. The next time you step outside on a clear night and look up at that vast, hazy band of the Milky Way, I want you to remember that you aren't just looking at serene points of light.
You're really not.
You are looking at billions of ongoing, brutal cosmic tug-of-wars. You are looking at countless planets fighting a losing battle, their internal batteries dying, their invisible atmospheric shields being actively shattered and swept into the freezing void, leaving nothing but cold, dead rock behind.
You are standing at the bottom of a fragile, perfectly balanced ocean of gas that has miraculously survived a 4 billion-year thermodynamic assault.
It is a profoundly sobering perspective on our place in the cosmological timeline.
Completely changes how you see the sky.
But I want to leave you with a final, lingering thought to ponder, a question that builds on the mechanics of radioactive decay and our position as early arrivals in the universe.
Okay.
Think about the ultimate fate of the cosmos. If a planet's long-term life support system, its volcanic engine, relies entirely on a finite supply of heavy radioactive elements like uranium and thorium, forged in ancient neutron star collisions. What happens in the deep future?
As the universe ages, star formation will inevitably slow down.
The giant supernovas and neutron star mergers will eventually cease entirely. The universe will literally lose its ability to forge new radioactive fuels.
And as the existing isotopes slowly decay into inert lead over trillions of years, the galactic fuel supply will run dry.
So, billions of years from now, will the very last generation of rocky planets formed in this universe be born entirely dead, utterly devoid of the radiogenic battery needed to power their mantles, physically barred from ever exhaling an atmosphere, and forever incapable of supporting life? Until next time, keep looking up.